Alright, hell yeah. So this problem got me derailed because I didn't know how to use summations. So this is summing the product of two different numbers, and then this is summing the individual numbers separately and then multiplying them together. So these two things do not equal, and I was using this in place of this. This, you have to multiply both these numbers together. And let's do a scenario. My brother's like, hey, let's have x equals 1 and 2, and then y equals 3 and 4. And so if we, and this is going to be I equals 1, I equals 2. And so for the first sum, we're going to have 1 times 3, and then we're going to add it to the product of 2 times 4. And this is going to be 3 plus 8, which is 11. And then let's see what we do over here. This is summing all the x's, 1 and 2. So we're going to have 1 plus 2, which is 3. And then we're going to multiply that by the summation of the y's. 3 plus 4. 3 plus 4 is 7. And then we're going to have 3 times 7, which is 21. So 11 does not equal 21. And hopefully we even did the arithmetic right. We can double check fairly fast. So 1 times 3 is 3, and we're going to add it to 8. 3 and 8 is 11. This is adding up all of the x's first. This is going to be 3. This is going to be 7, and then multiply them together. 3 times 7 is 21. So those do not jive. All right, so hell yeah. So this really isn't a problem in this book that we're going to, you know what I mean? It's so this is James Stewart, Calculus, Early Transcendentals. And it's the chapter on, it's just kind of first chapter stuff. This is just linear regression and fitting curves. And so what they do is they just come up with a solution. And alright, so their solution is this equation. And so that equation is this. And then how they just said that they used a calculator, a computer algebra system, Excel, etc., and used the least squares method. And so that's what we're gonna do today. We're gonna solve this using the least squares. Now I could have solved this in like 10 minutes had I done everything correctly, plugged in the right numbers, but this was my main mistake. And I couldn't figure out this mistake until, hours later. I spent basically all day, kind of going through it, making sure the math made sense, making sure my numbers were accurate, and I was just using a faulty equation. I was using this instead of this. Alright, so hell yeah. So let's talk about, because this problem was cool because I get to use my linear algebra skills. I learned linear algebra just like last year, let's say. And hell yeah, that's what we want to do. Okay, so linear, and before that, what we're gonna look at is that this fits it's like a parabola. And so the equation of a parabola is going to be, some sort of constant, and we're going to label this a2 x squared plus a1 x plus a naught. So this is a quadratic equation, and cool. And so what this problem is a ball is being dropped from the upper observation deck of the CN tower. So it's 450 meters. I'm just going to quickly multiply by 3. I'm going to do that in my head. So it's like 1,500 feet above the ground. And its height above the ground is recorded at 1 second intervals. So when we start out at time 0, we're going to drop a ball from a height of 450 meters. After 1 second, it drops 5 meters. That's a classic one that you should do when it comes to using the acceleration of gravity as 10 meters per second squared. Don't write it like this. Write it as 10 meters per second per second. You know, you do the units like this. You can even put a 1 down here. You can even say this is a change in velocity for every 1 second. So after 1 second, your velocity goes from 0 meters per second to 10 meters per second. You have an average velocity of 5 meters per second. For 1 second, it went 5 meters. So that is one of those things that you should just have, you know what I mean, just totally be able to spit that out. Use acceleration of gravity as 10. It's close enough to 9.8, and it just makes your intuition just a lot more solid on that. Okay, cool. After the second, what should we, you know what I mean, we're going to go from 0 to 20 meters. Average speed of 10. We did it for 2 seconds. We should be 20 meters lower, and that's what we see, 450 to 431. Cool, you know what I mean? And after 9 seconds, we should be going from 0 to 90 meters per second, average speed of 45. We did it for 9 seconds. 45, I'm just going to guess, 50 times 10, 500 feet. We should be basically at the bottom. 45 times 9 is 405, and that's what we see. 450 minus 405, and we're about 45 feet, you know what I mean, at 9 seconds. Now they're going to use, you know, acceleration of gravity for this as 9.8, you know, so that's the discrepancy. But if you use 10, you can get intuition, just your intuition is just a lot more crispy on this. Okay, hell yeah. So, and then when modeling, you know, I mean, if we're going to find an equation for this, we have 10 different data points, and this is where, let's say we had a data of 2 points, there and there, and we wanted to fit a linear line. Well, we can fit a line that goes through those 2 points. There's no reason we wouldn't do that. If we had 2 data points, you know, x and y, then there's no reason that we would put the line over here or the line over there. If we had 3 data points, you know, one is offset, but we still knew this was kind of a linear relationship, well, we got a couple options. We could put the line through those. We could put the line through those. We could put the line through those. So we kind of have 3 different lines that would actually go through at least 2 points. Or we could say, hey, I don't want the line to go through any of these points, and I'm just going to, you know, do that. And then so that's kind of what we're going to look at today. And how do we quantify that? How do we quantify that this was a good fit? You know what I mean? I mean, just from observation, it seems like, well, like that's a poor fit. That's a poor fit. A line that goes between these 3 seems like a good fit. Now, is there a scenario where we could come up with where, you know what I mean, that point's right there, but we don't want to fit, you know, we don't want to be perfectly down the middle, where it makes more sense to be closer to this one, even if we're, you know, let me draw this a little bit better. So if I have, so here, and I'm going to draw a big offset, and I'm going to go kind of halfway. Let's say we were going to do a trend line down the middle because we have a point there, and then a point there. For this combination, maybe it makes more sense to be closer to this one and a little bit, so we're going to go in a little bit on this one and a little bit closer to that one. I really can't tell from this and from intuition whether that would improve this fit or not, or if I have 3 lines halfway down the middle would be the best. I actually don't know. From an intuition perspective, I don't know. But what the error is going to say is just like, well, like obviously you missed this by that much, and you missed this one by that much, and you missed this one by that much. And let's say these are all just values of 1. And so if I could just reduce this and then make this line go through this point, hey, that point goes to 0. So that's better. And then I could still have it go, you know, let's say I could go kind of right in between these 2 points. So it's still going right there. And so this, the error here of this line, you know, when it comes to that point, isn't too much different. Oh, yeah. So let's, this is kind of fascinating to me. So let's kind of walk through that. All right, hell yeah. So let's see if we can, we're going to set that up and see if we can get some intuition going. And that's honestly one of the skills that I would like to improve and work on is, can you set something up? You know, if you have a question, you know what I mean, can you set it up where it's going to make sense? All right, hell yeah. So here's the point right here, and then we're going to, from my picture, what did we do? We said one point's right here, and then maybe the other point is right there. And so if we did a trend line right here, the error is actually, hey, this point has an x, so this is, let's say this point number 1, point number 2, and point number 3. It has an x value of x1, y1, and this has an x value of x3, a y value of y3. This has an x value of x2, y2. And so the x value is going to be right there. This x value is going to cross right there along this x-axis. This x value of x3 is going to cross right there. If I'm saying this is my prediction, so I'm going to get an equation for this line, y is equal to mx plus b, then I know that it's not going to run through that point, or that point, and so this is going to be what I'm going to call the error. I'm going to be like, well, if I threw in an x value of x1, this equation is going to give me this value. It's going to give me that value right there. And I want it to be this y1, because if I did an experiment where I was getting these values, like these are the values that I would want this equation to be closest to. And so so this is the error. And so let's make it make a little bit more sense. Let's go to this x2 position, and the equation. So I like to think, even though, like, even with this problem, is like, sure, there's going to be a lot of math to get a fit equation that's going to be y is equal to a2x squared plus a1x plus a naught. But I think for problems, it's useful to be like, well, cool. Let's say there is a mathematical way to get this equation. Let's just say I got the equation. So what does that look like? Well, if I actually get the equation, I'm going to have some number for a2, x squared, plus some number for a1, x, plus some number. Cool. And let's say I just have that. And then once I have that, then, you know what I mean? How do I check that that was a decent fit? And so that's what we have right here. I'm going to say, hey, this is the equation. I'm going to say this is y is equal to a1x plus a naught. And see how this linear equation is just minus the kind of the second order component, a2x squared. And so I could say that this equation is just, you know, some number times x plus some number. And I'm just going to say that we got it. You know what I mean? So I'm just going to say, and that's the equation that we got. And I want to, and so now we're going to look at, yeah, so that's useful. Okay, so let's plug in our x2 value. This equation is going to be this value right here, where the point that we wanted it to hit was up here. You know, so this y value right here, this y value is this equation. This y value is when we throw in, or this y value is just an experimental data point. We already know what it is. And so here's the error here. And then so if we do, again, for x3, we're going to go to x3, put it into our equation. We're going to hit that point. Our experimental data is this point. There's a difference between them. And so here's the error. Let's say this is just visually 1, because I set it up where all of these are the same. And then I want to know, just from an intuition perspective, what if I had the line go through this point, and then it could go anywhere in between these. And And let's just, to make this even simpler, I'm going to have it go through this point because that'll still have an error of 1. If I go through this point, this error will go to 0, and then this error will increase. But what will we realize from this is that this would be a better fit. So if this is my new line, y is equal to x, a number prime x plus just another, I'm just going to say this is just a new equation that's better. The error here, because my experimental data point's right there, this equation that I came up with goes through that point. There is no error, so the new error there is 0. The error here is going to be the same because my experimental point is right there. My equation goes through that point, so I have an error of 1. And then right here, my experimental point's up there. This line is way down here, but let's say that error isn't too bad. It's just 1.5. Okay. So this is how the least squared works. It says, when we thought this was a good fit, we had an error of 1 here, an error of 1 there, and an error of 1 there, and we had 3 data points. And so that was a total error of 1 plus 1 plus 1. That was a total error of 3. If I made a better line, that I thought was a better fit, we had 0 error here, error of 1, and an error of 1.5. So now our error is reduced to 2.5. And that's it. That is all least squared is doing. It's saying, hey, let's modify where this goes through. And with 3 lines, we have 3 different locations that this line could, go near this point. It's going to come, you're going to have some sort of distance that's going to be off from this one, some sort of distance that's going to be off from that one, and some sort of distance is going to be off from this one. As we get closer to this point, this error improves. As you've seen, as we got farther away from that point, this error got worse, but maybe one of the other errors got better. Alright, hell yeah. And let's just work on our intuition and turn the camera off and on. But I was just like, well, let's say this is an outlier, and let's just go through these 2 points. Forget about that point. What's my error? My error now is 2. Hey, that's literally the best error that we've gotten so far. And then, what happens if I move, up 1? This reduces by 1, but I increase these by 1. So it actually is very useful to go through, these 2 points. And, yeah, that's fascinating. And so I'll turn off the camera and to see if I can see, intuitively a better line than just going through these 2 experimental points and just considering that an outlier. Alright, hell yeah. And I'd actually just rather do this problem, you know what I mean? And then, because maybe we can find a stopping point. I introduced the fact that we do have this problem, that we want to get a line fit, but this was just kind of a fun exploration problem of looking at a linear equation with 3 points and just kind of seeing if we could find a better fit. And so what we're going to do is we're actually going to reset up this problem. And yeah, I'll just probably try to get some fresh sheets of paper. Alright, hell yeah. And I think what I'm going to do is I'm just going to have this be the origin, this be 4 and 3, so kind of like a 3, 4, 5 triangle. And then this position be 3 and 4. And then I want to know the line that goes through there. So that's what we're going to do, and we're going to use least squares. Hell yeah. Because then we can kind of talk about, what we'll get is the actual solution to this that will maximize the error. We talked about how we had 3 points, that we're going to have 3 different accumulations of error, and we want to reduce that number. We could reduce it by 2 just by going through that point, and maybe we'll go back to seeing what the error actually would be. So I'm going to have 4 and 3, and then I'm going to go 3 and 4. If I did put the line right through there, that line is going to have a slope of rise over run. So this line is going to be y is equal to 3/4 x goes through the origin. And then this value right here, if I throw in x is 3, y is equal to 3/4 times 3, which is 9/4 which is 8/4 plus a fourth, which is 2 1/4, which is 2.25. Hell yeah, so this value is 2.25. I'll just kind of write that in. This value up here is 4, so that error is going to be 4 minus 2.25. And yeah, since this is higher than 2, and then we're gonna be less than 4, so it's gonna be, that error is going to be 1.75. Hell yeah, so in this example our error is 1.75. What I want to know is if I take this line and then shift it some different place, could I reduce the error? And I know that this equation is going to be in the format of a1x plus a0. And so, and this is very useful to be like, hey, let's say we just have the equation. That's what we did here. Once we get the equation that we think is the best, then how do we know that it's, or how do we look at this and see what error it does have? We know that it can't go through all 3 points. So then how do we use this to quantify its error? It's like, how off is it? If this line was way down here, it'd be like, whoa, this line is way off. Let's bring it up to there. That's getting better. And so we do that by saying, well, we had an error here of 0. We had an error here of 0. And we had an error here of 1.75. If I could modify this equation just by a little bit, let's say all I did was bring this equation up by 1, and let's do that. Y is equal to 3/4 x plus 1. And when learning math and physics, I would say if you're not able to just do, like, this is a full separate problem. The fact that I said, what if we just increase this by 1? Well, get ready, because now we're setting up a full separate problem that, will have an answer in the back of the book. You can make errors, you might get stuff wrong. But I think this is a good skill to use, to ask a question, set it up mathematically, and do it. Even if you have to do 10 of these little problems before your intuition kicks in. Okay, so if I increase this to 1, I just know, I can visually see that the error there, the new error is 1. If I boosted this one up, shifted it by 1, the error here is 1. And then if I shifted this up by 1, the error gets reduced, so the error here is going to be 0.75. The total error, the error prime, this was just a single value, but if I said the summations of error 1 plus, and you wouldn't say it like that, if I said the error total is equal to the error 1 plus error 2 plus error 3, and in the first case, we had 0, 1.75, and 0. So 0 plus 1.75 plus 0 was 1.75. If I shifted the line up by 1, our error total for this new equation was going to be 1 plus 0.75 plus 1, which is 2.75. All right, hell yeah. So that was worse, but you know what I mean? So maybe we don't want to shift it up. If we shift it down, it would have got worse. So then you're just like, well, that seems like the best, because if I shift it up, it gets worse. If I shift it down, it gets worse. But that's not the only variable that we can change. We can also change the angle over here. If we change this aspect of the slope, there's a chance that both of these points reduce an error, and this one didn't change at all. And so, I mean, just based on this. All right, hell yeah, new battery, and then we're back. And I honestly can't tell. Like, the fact that I made these points, you know what I mean, just kind of like a 1 unit high, 1 unit over, but here's our 2 data points, and then this being this far away. I can't tell when I angle this line, if I was going through these 2 points and I started moving closer to that point, whether that would improve. You know what I mean? If I did it in Excel, I could have this line, and then all I would have to do is just increase the slope by a little bit. And so let's do that, because even though we don't have Excel, this is, our original equation was 0.75x. And so I just want to know, I want to know if I do a new equation of 0.7, we'll just do 0.8x. If I did 0.8x, do things get better? I'm still going to go through this value right there. And I just want to know if the error increases. So my x values are x equals 0, x equals 3, and x equals 4. So if I throw in 0 here, I get y prime of 0. And the prime is not a derivative, it's just, I'm just saying, hey, we're just had a new. This was the first guess, this is going to be a new guess that hopefully is better for a new equation. And so that one is 0, x3 is going to be 0.8 times 3, and that's going to be 0.24, 2.4. And then times 4 is going to be, 4 times 8 is 32, 3.2. And so, and our values are 4, 3, and then 3, 4. So our error here is a difference of 0. And we're just looking at the absolute value. So I'm going to say the error is the absolute value. So the error total is going to be, the absolute value of the error 1, error 2, plus error 3. And we haven't even put equations on these. We're just saying, hey, this is my experimental. So if we do this one, this is my experimental point. It's up 4, and this is the value that I got. So 4 minus 2.4, there's a difference of 1.6. So that's going to be error 2, error 1 is 0, and then error 3 is going to be a difference between 3 and 3.2. It's going to be 0.2. So now our error total is going to be 1.8. Is that better? No, that is worse. So it seems like this is the, there's a chance that this is the only value that that is the best. And so, and maybe I just don't see it to where it shouldn't. Because, we just adjusted one thing. We had the value go through here, and our errors got worse, but we could also increase and lower this. And so which error got worse? Like error, the second one was, well, that got a little bit better. But this one got worse. So maybe we would want a steeper angle, but then lower it. You know what I mean? So maybe we would actually want, so let's do a new equation that's 0.8x, but then we want to drop it by 0.1. You know what I mean? We're going to get an error here of 0.1, but maybe those other errors will get better. And this is where it's like, I don't even want to do this. You know what I mean? But that's the whole idea, is just like being able to experiment. So it's not that hard. We have the value where we throw in x is 0. That's going to be 0.1. We already know our error 1 is just going to be the difference between 0 and 0.1. That's our error for this error. So y at x is equal to 3 in this equation. We're going to have 2.4 plus 0.1 is going to be 2.5. And then the difference here is going to be 4 and 2.5 of 1.5. And then our error 3 is going to be this equation where we throw in a value of 4. So 4 times 8 is 32, 3.2. It's going to be 3.3. And then we're going to have 3.3, and our difference is going to be 0.3. So this is 0.3. And then our total error is going to be 1.9. So that got worse. So I don't know. So let's do this mathematically, and maybe, the best fit is actually just right through those 2 points. And I think because we experimented so hard with this, that if that is the case, if I have any points where you have the farthest points away that are like that, and if I have any outlier outside, that the best fit is always through the outer. I don't think so. I would and this is where I actually want to pause the video and to be like, well, shouldn't I be able to prove this? Like, couldn't I take this to the extreme and figure out that, like, this isn't, yeah, so I'm gonna run, and I can just do it right now. The thing that I can think of is an isosceles triangle. That would be, where if this is my line of best fit, that means that the error here is just the height of the triangle, where if I went to a height of halfway, you know what I mean? Now I'm having, well, actually that line's the same. Oh, and you know what? Well, and this is a bad example, because only if this is a flat, only if these two data points have a slope of 0. Yeah, and I remember this maybe from kind of linear algebra, where, or I don't know, like it seems like the error here, if I put the line through there, the error, let's say that height is 1, but if I put the line at halfway, the error here is 0.5 and 0.5. So there is, oh yeah, this is tripping me out, because I think this is the best fit at the halfway point. I just can't, I can't tell why it's not here, going through both those 2 points, and that height being a height of 1. You know, both those have the same amount of error, and they're equally justified. But maybe if you actually square the error, because the error here is an error of 1, so 1 squared is 1, if I just had the line going through here. But if I had the line going halfway, I would have 0.5 squared plus 0.5 squared plus, and this would be and this would, never mind. I don't know what I was thinking. If I had the line go through there, my error is 0.5, 0.5, and this is 0.5. So that's more error. So yeah, because I was, that's fascinating. When you make a mistake visually, and then you just think a mathematical equation, you know, doesn't apply or something, where it's like usually the answer is you just made a mistake. So if I do have the line going through the halfway point, I have 0.5 error there, 0.5 error there, and 0.5 error there. If I have the line go through these 2 points, my error gets reduced to just 1. And it doesn't matter if I square the errors. You know what I mean? So 0.5 squared plus 0.5 squared plus 0.5 squared is always going to be greater than 1 squared if I just have the line go through there. And that's not the case either. Alright, hell yeah. I am hoping I'm learning something today. Like, you should always be like, hey, I'm making a mental mistake. Something that, you know, I intuitively am saying that this should be a line of best fit. It has a total error of 1. If I put this line right here, it has a total error of 1.5. But when we look at lines of best fit, it's always the error value, like the error 1, error 2, error 3, and you square them. And the only reason I thought you squared them is just to get the value to be an absolute, get it to be a positive value, because I really want the absolute value of the error 1 plus the absolute value of the error 2, and the easiest way to do that mathematically is just square it, and the sum of the squares of the error will be, if I minimize those, I also minimize, you know, just the errors in general. But is that not true as well? I have to go back and maybe that's not true, because that's where I'm getting, you know, I just set up one example where that's not the case, where if I minimize the error squared, and I should do a couple of these, just to see where the line of best fit actually goes through. But yeah, the error squared here is going to be 0.5 squared plus 0.5 squared, because these are my 3 value points, and then here is the line going through the middle, and it's going to be plus 0.5 squared, which has an error of 0.75. If I reduced it to here, let's say I did 0.4 squared plus 0.4 squared plus 0.6 squared. That's a lower error. And so then let's keep going. I'm going to go 0.3 squared plus 0.3 squared plus 0.7 squared. And that is a lower. So how about 0.25 squared plus 0.25 squared plus 0.75 squared? And that's higher. Okay, so 0.33 squared plus let's do 1/3 squared plus 1/3 squared plus 2/3 squared. And that gives me the best. Okay, so I didn't even realize that visually, that the line of best fit, if I have this, is at 2/3. So it is a weighted, so it's weighted. And because these 2 points down here, a line of best fit is closer to them, and it's weighted by, we have 2 points, and maybe it's weighted by, I think that's about it. If you have a triangle, I think it's just the height. It's like geometrically, it's going to be 1/3 of that height. And so that's what I'm seeing, that this line of best fit will be 1/3, 1/3, and 2/3. But I'm just so glad I did this before running through the math, because you only get that opportunity once. You only get the opportunity to play around with something before you just run a mathematical equation and then it spits out that the line of best fit will actually be a slope of 0. So we're going to have a1x plus a0 to be 0x plus 1/3. For this scenario. Like that's what this scenario would show. And so if I go back to this scenario, and then I even learned something, that the least squared, and that's why I really don't mind making mistakes and posting videos that are absolutely wrong, because more commenters are going to be like, oh, no, you made a huge assumption that the least squares, when you take the error and then you square it, so if this is the error of 1 and you square it and then you sum with all the other errors, etc., this is going to be the sum of the square of the errors. You get a different value than had you just ran the problem where you just wanted your errors to be minimized. And so, let's go back, because if we did that 1/3, our errors are going to be 1/3 plus 1/3 plus 2/3. Our errors are going to be 1, and that's the, and we just, but because the errors squared give us only one location, but if we just have the errors, the error total be 1. This line could be anywhere. Anywhere between this is going to have an error between these points of 1. But what's happening is that this point has more weight to it, because these 2 points are, are down there. And so, yeah, so that's I'll have to look into that. Or just Google. I'm going to Google right now. Is the squared portion of the least squares important, where lines of best fit don't just minimize errors? Hell yeah. Hell yeah. So we're going to end the rest of this video, from looking up Google questions. I've already looked up all these, and I found out that squaring the errors is a fully separate process, and it's not just to get positive values. You know what I mean? And so, and there's times where, and so let's read these questions. It says, do lines of best fit using least squares just minimize the sum total of the squares of the errors and not the sum total of errors not squared? It says, it's really difficult to actually read this, but I was just like, are we saying that when we find the errors and square them and then add them all up, we get a value? Do lines of best fit using the least squares just minimize the total sum of the squares of error, and not the total sum, and not the sum total of the errors not squared? Yeah, so yes, the line of best fit using the least squared only minimizes the square of the errors themselves, and that's a unique property. It's not just, yeah, I thought they converged at the same spot. I thought like from a almost like a calculus perspective, or like kind of squeezing them in or something, that if your errors get real small, squaring them, even becomes a smaller number. And so yeah, that was what I was thinking, but that's not the case. So this only minimizes the square of the errors and not the sum total of the errors themselves. This is because summing the raw errors would, and they chalk it up to just this positive and negative thing. But I was just like, nah, I get that. So I'm just like, well, what if I'm, let's say I was able to use absolute values. So I'm finding that if I take the total sum of the absolute values, so now I'm just getting a line of best fit. I know that I have errors, and I'm just going to take the absolute value of those errors, and I want to know that value. So sum of the absolute values of the errors and minimize them for a linear best fit. And I just want to talk about linear because that's what we had the 3 points. Using 3 experimental data points, I get a best fit line that passes through the 2 farthest away points, and that's not necessarily true either, because you can go through any 2 points. But yes, it says you are finding this result because a fundamental property of the least absolute deviation, that's when you don't square the errors, you get this term LAD, least absolute deviation, and it's a form of regression. I can't even tell you what the definition of regression is, but finding a fit or something like that. Regression is that the best fit line is guaranteed to pass through at least 2 of the data points. So if I'm using 3 points, because that's what if I'm using 3 experimental points and I'm using least absolute deviation, this is just a fact that line will go through 2 of them, because what this process does is it says one of those values is an outlier. So once we get to this last tab, that's kind of the general gist, is that when we do experimentations, our sensors aren't very good. Like the free-falling ball, hey, we might be off, and that's why we get a deviation of the points. And then even if we get any deviation from exactly, what the physics in an environment is doing, then and we're not talking like wind and other things like that. We're just talking like, hey, from a physics perspective, I could set up a purely physical experiment that from, like, if these are the only things in the universe, forces and a chunk of mass that's a point mass, like this is going to happen. But then when we go to measure it with, the best tools that we have, we're still going to get deviation. And that's going to be a little high, a little bit low. And so, And so a little bit high means that's an outlier. That point is now just an outlier by a little bit. But a little bit low, that's also an outlier. But all the points are outliers. But if all the points have roughly about the same error, cool. You know what I mean? No big deal. If one of the points from the data center or from the sensors, recorded too high, and then one over here recorded too low, this process, the least absolute deviation, because it's not going to be easy, because it's not mathematically, you can't just use derivatives, and so that's what we're going to learn in about tab 2 or 3. But yeah, you can reduce those outliers. This process will be like, sure, some of those values are outliers, and this is a process to reduce those and get a better fit instead of having that outlier be the same weight as all the points that actually look like they fit. And you can just do a visual and throw those away, but you can also say, hey, you know what I mean, in this experimental process, I know that my values are going to be a little high and a little bit low, and Yeah, so cool. So when should I use the least absolute deviation regression? And it says you should use it when it contains outliers. Cool, so we talked about that. Heck yeah. So now let's see what this process looks like. When will the least absolute deviation, that's the one with outliers, be a better fit? Best fit be the, well, when is that going to be the same equation as the least squared? And the LAD, the least absolute deviation, and the least squares equation are the same when there is a perfect fit or no outliers in the data. So that's interesting. The fact that even with our problem, and you know what I mean, we can pull this up, with our ball. Whoop. Oh, bummer, dude. Sorry about that. You know what I mean? All these data points, these are outliers. So I think that actually is a pretty good. The only way that this is going to be a perfect fit is if I have a quadratic equation that hits all of these points. And you know, so that's where there is no outliers. So there is going to be a difference, because even just the equation that we get, there's error here. And so let's talk about that, because I could do this complicated process to get a different equation that accounts that all these experimental points are a little bit high, a little bit low. But yeah, cool. So let's take a look at what we got. So is there any mathematical ways to find quadratic best fit for least absolute? Yeah, and I just want to know if there's a mathematical way to do that, because maybe before it said you can't, you know, you can't use it. So it says least squares, mathematical convenience, because it's differentiable. You know, I mean, you get a closed form mathematical solution using, you can use linear algebra. That's what we did. But this, I don't know how to do this. You know what I mean? But this is the setup. So this is, yes, you can set up a quadratic best fit for least absolute deviation by setting up an optimized problem and solving it using methods like the simplex method. I didn't actually research that at all, because there was another method that was iterative. And if I see the word iterative, I think I'm super happy about that, because once you run one iteration, usually the iteration is like getting you closer to something, but based on general assumptions. Like you're assuming something, and then let's just run it. We get closer to the answer. I'm going to use that answer as my new inputs, and then using kind of the same general assumptions. In an iterative process, I've always felt that you can have a better understanding of what's going on. So that's the one I looked up. Iteratively reweighted least squares, IRLS. First time I've ever even heard of this. How does iteratively reweighted least squares process work? And this wasn't even a very good one, but you first have to solve the problem using least squares. Cool. So you're going to get that. That process is the same. I mean, you got to get close, right? So that's probably the closest way. Use least squares mathematically to get a fit and get an equation. And then you're going to adjust using new weights. And so so that process, I was like, well, show me. And so hell yeah. So here is our data points. Point 10 is going to be the potential outlier. Let's say so we start, and when you get a solution, you're going to have three equations, three unknowns for this. Even though you have a boatload of coefficients. Well, no, it's a summation, so you have, but anyway, yeah, that's kind of interesting. But yeah, we use linear algebra, and as long as you use summation symbols, it looks like three equations, three unknowns, even though each of those three equations involves summations, like doing the same equation and adding the errors and stuff like that, the square of the errors. So anyway, yeah, but it's still three equations, three unknowns from a matrix perspective, and then you're going to get your A, B, and C values. And so hell yeah. So this is that first step. You're going to get those values, A, B, and C, using, you know what I mean, just basic equation. You have a bunch of equations, a bunch of unknowns. You have enough unknowns you have enough equations for the unknowns that you have. And in that process, if we did set it up with matrix, W is going to be the identity matrix, and that's going to be what we're going to use as our weighted matrix. So this W matrix is going to change, and then we're going to figure out why it would change. And it says down here, commonly we're going to use 1.349 for 95% efficiency, and I'm just guessing on this. I'm just going to guess that because you're just assuming that your stuff ain't going to be 100%, right? And so you have to be like, well, how wrong is it? You thought it was pretty good. And so this is going to be like, hey, we actually have a lot of outliers, or hey, we for our problem is like we thought we did pretty good. You know what I mean? Pretty good, but maybe we're 95% good. And so what I just said right there is probably just total garbage, but I'll have to look this up and run. And I don't know if I could even find simple problems doing this because it's fairly complex. But cool. So I'm going to use that 95%. I'm going to use it in this equation where K is 1.345 for something that has an efficiency of 95%. I don't even know what S is. I don't even know what RI. I guess RI is right here. Does it even for some of these, well, it's like, well, it has to, it probably said what S is. Nope. I don't know what the S is. Anyway, but you get a value, and we're just going to use 1 if that value is less than 1. If that value that we got right here is less than 1, hey, our new weight is just 1. I think only if our new value is greater than 1 for this number, then we have to use this weight that's going to be a proportion. So the identity matrix gets reduced by it's going to be 1 divided by a larger number. So this number is going to be a number smaller than 1, and that's going to be the diagonals of that identity matrix. And so, what that does, what they're saying it does in this equation, is it's going to reduce the weight of the outliers. And so that sounds cool. I don't know how it does it. I don't even know where this equation comes from. And I hate this when they're just like, hey, let's throw this S value, and they don't tell me what and S is a robust estimate of the error standard deviation using the median absolute deviation. So cool, that's what S is. And brutal. I don't know any of those terms mean. But I do know with this linear algebra, and yes, if we modified this, it's going to say, or they're saying that this equation reduces, it deweights, it downweights the outliers. So when we do have an error due to an outlier and we're trying to reduce it, we really don't have to reduce that error a whole lot. It's almost like that thing doesn't exist out there. It only partially exists at 95% of it. And anyway, I'm just saying words because I've never done this process. But there you go. And then so you run it again and you get new values, and then those new values are going to be part of a new equation, and then you're going to have new error residuals, and this is your linear. This is your LAD residual. It's not this is your error. R is your error, and if you squared it, that would be the square of the errors. And that's just for the error for one. This is the equation that we found. This is our data point that we got from our data. We know it might be a little bit of an outlier, like some of them. Cool. And so that's this value right here. We're going to take those errors and we divide it. We divide it by a number that's greater than 1, so that makes sense. And then we and either multiply by S you know. So who knows? Yeah, and so S could be either greater than 1 or less than 1. And so therefore this number can either be, continue to grow, because S is also greater than 1, and this is 1.34, so S can be a little bit less than 1, where this denominator is still greater than 1, making this whole thing less than 1. And if it fits into that case, so whatever we get for our error here, and our error is an actual value. It's not a percentage. It's not a fraction of a whole. It's just saying, hey, we have a value from our equation, a value from our experiment. So that value, that number could be anything. And then we're going to divide it by, but if we divided it by 1, we would just get that value. Cool. But if we divided it by, and that doesn't even matter because this equation just says, hey, if this is less than 1, we're done. And if it's greater than 1, continue on with the new weighted matrix. Is that what it even says? So iterate. Return to step 2 with new weights and repeat the process until the coefficient converges or a maximum number of iterations is yeah, so you're just looking for this to stabilize, and if it does stabilize, cool. Yeah, so you're not, this might, oh, that's fascinating. And if your weight is 1, I don't know, maybe that does actually change your problem. I have no idea. I don't think so, because if your W is 1, then you're just this same equation where this is your identity. So only if this is greater than 1, and they're calling this the standardized residuals. Standardize the residuals. And if that is greater than 1, then you for sure are going to change that equation. But I don't think it's an on-off switch where at some point this value switches to where it's no longer. But I think wouldn't that make sense that if you're getting closer? I have no idea. I haven't run one of these. But yeah, as you're iterating, if this weight is always constantly, I don't know. Yeah, that's fascinating. I guess I don't think it would matter either way. But yeah, run enough iterations. You're just seeing if your equation stabilizes. If it stabilizes, cool. Or converges, then you have it. All right, hell yeah. So that's there you go. So that's kind of what I learned, because I thought when you squared the errors, you were just doing it to get rid of the positives and negatives and making all positive, but that's not true. You actually get a different value, and one, it can be differentiated, which closed form mathematical solution, so that's cool. But but it's not necessarily going to be reducing just the total error, and so that's fascinating. Yeah, so I actually want to run one of these, even on that problem, to be like, well, let's. Yeah, that's fascinating that you could change those. Values, and I've set this up in Excel where, cool, let's say I get the least squared solution of A, B, and C, and then I can just tweak it a little bit and see if my Excel data points for the total error for each of those data points, or the summation of the data points, reduces. And if I tweak this one just up a little bit, and I can reduce the overall error, then hell yeah, then I know that wasn't that wasn't the quadratic equation that reduced just error in general. It was just reducing the least squares of the error. And so that I might do it on my own time. But anyway, we're done with this. I haven't made a new one in a while. And I just get down rabbit holes, but this is the reason why, because like the second I start saying stuff where I'm just like, oh, I don't even know why this isn't true. Well, hell yeah, that's what Google is for. That's what AI, the fact that AI, you can type this in right now is just ridiculous. and I could get more examples. We could do that later on tonight. But anyway, this video is done, and we found out that yes, least squares is not just to get positive values and to reduce the errors. And reducing the errors isn't necessarily reducing just the actual errors between your data points and your values, because even using least squares that's fascinating. So I think I can say this correctly. When you use least squares, you are downweighting the outliers. Is that true? Nope. I think the opposite. If I have 3 points in our little triangle, using the lowest, I don't even know what the hell they call it, LAD? They call it ordinary least, they call it least absolute deviations. So if I have this triangle of 3 points, least absolute deviation is going through 2 of those points. Where if I use least squares, I'm always going to go through, and from an X and Y perspective, and if I have this triangle, it's going to go through 1/3 height, and it's going to be closer to the bottom 2. Because it's assuming that top one is an outlier. It doesn't know which one's the outlier, so that's also the weird thing. And it says you shouldn't be using least absolute deviation for 3 data points, especially if you don't know which one's the outlier. So that kind of comes up. So I don't know how to say that. Least absolute deviation will assume that one of your points is an outlier, where least squares just wants to kind of hit this midpoint. And if a point is an outlier, it's going to be more weighted than it should have been. Is that saying that right? It seems opposite the way that I'm thinking of it and saying it. But least absolute deviation helps to reduce outlier error. It's assuming that some of those values are outliers and giving them less weight. Where least squares is that where that weight of the identity matrix, you're almost giving it a weight of 1 at that point? I don't know. Or I don't know how much weight, and even in least squares, I could look that up. Is least squares regression giving even outliers the same weight as non-outliers? No, least squared regression does not give all data points the same effective weight. Outliers often receive disproportionately more weight, which pulls the regression line towards them. Okay, so yes. So least absolute deviation reduces outliers. So let's ask this. Does least absolute deviation is there more that could be done than least absolute deviation to reduce outlier error? Yes, more can be done than the least absolute deviation to reduce outlier error, such as using other robust estimation techniques like M-estimation or Windsorization, or transforming the data to reduce the impact of extreme values. Other methods include using more advanced statistical models and carefully removing outliers if there is a justifiable reason. This is so fascinating because my brother, when I brought this problem to him, he's just like, oh, this is what AI is doing, and this is how you can test AI, and this is how you train AI. Because you have all these outliers that, you might, and I'm just saying words of this, but hell yeah, you might want to reduce, you might not want those to have equal weights. So hell yeah, so there's other better techniques. So is least square regression bad if I know there's outliers? Yes, using standard least square regression is problematic when outliers are present. Yeah, it's going to really mess up your data because outliers can severely skew the regression line leading into... Yes, okay, so if I know there is outliers, what is best? What is simplest technique for regression? And I'm assuming the word regression means putting a... So the simplest technique is to use robust models such as Huber regression. Is Huber regression only used for LAD? No, Huber regression is not only used for LAD regression. It is a compromise between LAD and ordinary least squares regression. Is Huber regression only used to balance LAD and least squares? No, Huber regression is not only used to balance LAD and least squares. It is a robust regression technique that combines the best attributes of both to be less sensitive to outliers. Where it serves as a compromise, it is also used more broadly for robust estimation in the presence of heavily tailed noise data. Is LAD a technique for regression, or does it have to be combined with more advanced techniques? Is a distinctive technique for regression that minimizes the sums of the errors, and it does not have to be combined with other methods. And so that's fascinating because I swear, like right here, it talked about the Huber guy standardizing the residuals. But anyway, I'm done. You know what I mean? I think we learned like lines of best fit, outliers, huge problem. Least squares sucks, more complicated, but least squares, if you do have a good fit, is just mathematically you can take a derivative and get a closed form solution. So that's the cool, and that's what we were working on, is working on our linear algebra skills. All right, thanks for joining me on this one. Booyah.